Guillaume, it's please go ahead.
Good morning to everybody. I hope you can hear me well. So I would like to welcome to this new issue of the IAP Friday seminar, Tanja Hinderer, who is assistant professor at Utrecht University in gravitational wave theory. So it's a pleasure to have her today. Tanja got her PhD at Cornell University under the supervision of Iana Flanagan. She then held successively several postdoctoral positions at Caltech with the Sherman Fairchild Prize Fellowship, at the University of Maryland, the Max Planck Institute for Gravitational Physics, Radboud University and the University of Amsterdam. Her main research topic is the dynamics of compact objects in situation of strong field regime, with a focus on compact binary coalescence as a very important source of gravitational waves, of course. Her research covers in particular the dynamics of black holes, the probes of their nature, as well as the physics of neutron stars, their equations of state, etc. She has been notably investigating tidal and resonant phenomena in the binary dynamics of neutron stars or black holes. She is naturally involved in gravitational wave source modeling and leads the work package on analytical models for massive binary black hole binaries with the LISA consortium. But today she will tell us about neutron stars, and more precisely probing dense matter physics with gravitational waves from neutron star binary inspirals. So Tanja, you may go ahead. You have about 1 hour, including questions.
Thank you very much, Guillaume, for this nice introduction. And thank you all for coming to this talk. It's a pity I couldn't come in person, but hope at least we can have an online discussion after the talk. So the plan for the talk is that I'll first give some basic motivation why neutron stars are so interesting. And they're interesting for many reasons, but I will focus in this talk on extreme states of matter at very high density. And then I will discuss how can gravitational waves probe this matter physics, and highlight that to extract this information from the data, we need a detailed theoretical understanding of the interplay of matter with strong field dynamical gravity. I will also highlight a few things we have learned from recent discoveries with gravitational waves, and then end with an outlook to the exciting future that is ahead, but also the challenges that still need to be addressed to take full advantage of the upcoming new data samples. So let's start with very basics of neutron stars. They really represent the densest stable configurations of matter that we know of in the universe, where gravity compresses the material up to several times the density of an atomic nucleus. And this is an incredibly high density, which means really the matter is on the verge of, if you were to compress it just a little bit more, it would collapse to a black hole. And consequently, these states of matter represent really far extrapolations from any well-established physics. So there are still many questions about the nature and properties of matter in neutron stars. What is clear is that quantum physics is by far not enough to describe them. They are really dominated by the subatomic strong forces. And we do have some idea of the interior structure of a neutron star. So the first thing to note is that neutron star matter going from the surface to the very high density interior, that covers nearly 10 orders of magnitude in density. So it's an extremely vast range in density, not found anywhere else in a single object. So that also means there's a rich variety of different physics that plays a role at different densities. And this I'm not going to show here. I'm just showing in a cartoon version some of the very coarse-grained features. So already the crust of a neutron star, the outer parts, are very unusual forms of matter because the densities are already so high that the familiar structure of matter being composed of atoms, that already no longer exists. Instead, the crust is a lattice of neutron-rich nuclei. And as one goes more towards the interior, it actually becomes favorable for neutrons to drip out from the nuclei. So eventually, matter is mainly a uniform liquid of mainly neutrons. But then, if in the interior, the density gets above maybe 2 times or so, this is quite uncertain, the normal nuclear density, what that means is that the neutrons are so closely packed that they significantly overlap. And that means it doesn't make sense anymore to describe the matter in terms of interacting individual neutrons. Instead, one has to take into account their quark substructure as the new relevant degrees of freedom, and there might be a transition to deconfined quark matter. And interestingly, this kind of density range of a few times the normal nuclear density also happens to be the range where we could expect new particles like hyperons or some other particles to appear in neutron stars, which these particles normally only form at accelerators at very high energies and are very short-lived. But in neutron stars, they could be stable and form some sort of condensate state before there's a transition to the fully deconfined quark matter. So all of this is still open questions, but that also makes neutron stars very good laboratories for probing matter in completely unexplored regimes. And the importance of this is illustrated here again very schematically in terms of a phase diagram of quantum chromodynamics, or QCD, or the gauge theory of strong interactions. And the diagram shows temperature versus baryon density. So in everyday situations, we are kind of in the lower leftish corner of this phase diagram, where quarks are always confined into hadrons, and we never see any deconfined quarks in normal situations. But we know that at very high temperatures, for example, in heavy ion collisions, or also we think in the early universe, quarks can actually become deconfined and form a phase of matter called the quark-gluon plasma. And this has many, many interesting properties. And there are dedicated experiments trying to probe, first of all, the deconfinement transition, but also the properties of this quark matter phase. So here, for example, these collider experiments, FAIR and NICA, are 2 upcoming dedicated instruments to probe a different part of this phase diagram. But there's also a different range of this phase diagram where we might expect to encounter deconfined quarks, and that is at low temperature but extremely high baryon density. And in this case, we don't expect to find a quark-gluon plasma because really it's near the ground state, so the interactions between the constituents really dominate. And instead, what the phase of matter is called that exists or is expected at extremely high density is called a color superconductor. What that means is that the quarks are deconfined, but the degrees of freedom of the quarks, the color, flavor, and spin charges, are pairing correlated similar to the Cooper pairs of electrons in metallic superconductors below a critical temperature. And then at finite baryon density, there might be, not all the pairings might be fully paired. So there might be cases where small changes in the temperature and density could lead to a different phase becoming energetically favorable, or there are also some quark matter phases that are not color superconductors that have been theoretically proposed. So potentially the neutron stars can probe a very rich phase structure of this QCD diagram. And these kinds of phases of matter are only accessible in neutron stars or their mergers. And of course, this would be interesting in itself, but it also would have much broader repercussions for our understanding of fundamental forces of nature. And in particular, the strong interactions, which have very unusual properties compared to, for example, gravity or electromagnetism. For example, the strong force is weak at short distance and becomes strong at larger distances, completely opposite to gravity or electromagnetism. And furthermore, the vacuum also is non-perturbative, so it has important consequences. And in fact, this is responsible for most of the mass of visible matter in the universe, where the Higgs mechanism that gives masses to leptons, like electrons, that contributes only a tiny, tiny percentage. So clearly understanding QCD is quite important for our understanding of matter in the universe and fundamental interactions. So this is one of the important roles of neutron stars, but they also have a second important role, which is as probes for the emergent phenomena that occur at the nuclear or subatomic level. And this is because in neutron stars, all of the multi-body interactions are greatly enhanced and they probe a wide range of densities. So one can really study how do all of these constituents assemble and interact and organize themselves. How does that depend on density and the excess of neutrons over protons and so on. So this is also important for our understanding of how this subatomic structure emerges from the fundamental laws of physics. So clearly a lot of important questions to be addressed with neutron stars. So now let's discuss how can gravitational waves probe all of this physics. And before getting to that, let me just remind you about the features of gravitational waves from binary systems. And here shown for cases that do not involve any matter, so two black holes. And so as you might have heard before, the general feature of an inspiraling binary system is that there are two objects in orbit, and that generates dynamical distortions in the space-time curvature, which at large distances are the gravitational waves. And that takes away energy and angular momentum from the orbit. So the orbit shrinks, they orbit faster and faster. Eventually they collide. And for black holes, they then merge into a single black hole. And the time evolution of the gravitational wave signal is shown here in blue for an equal mass binary with aligned spins on circular orbits. And you can see below some examples of the fact that the detailed shape of these gravitational waves encode fundamental properties of the source, like the masses and the spins. So now the challenge is that given a gravitational wave observation of one of these signals, how do we work backwards to the source properties? And this is a very complicated task because this mapping between source and waves is in general obtained by solving the nonlinear Einstein field equations for the dynamical space-time of the binary system, which is extremely complicated and challenging. But over the last decades, a lot of effort has gone into developing approximate models that allow one to do the backwards inference going from features in the gravitational waves to source physics. And of course, at IAP, you have many experts who have been working on this and made important contributions. So then the idea is that these models are available and they can be cross-correlated with the data to find which one matches best. Of course, this is done in a Bayesian analysis and very sophisticated. So But the basic idea remains that the models are used to extract information from the source, from the data. So then now the question is, we clearly want to understand and model how do the effects of matter impact the waveforms. And in this talk, I want to focus on the inspiral part of binary neutron stars, or a neutron star and a black hole. And the reason is that this is the portion of the signal that detectors are currently most sensitive to. And also the effects are quite small, but they are relatively clean and they accumulate over many cycles of the waveform. So in the end, there can still be some net information built up. And in this inspiral phase, the effects of matter, as you can see by looking at the blue waveform, which contains a neutron star, and the gray waveform, which does not contain a neutron star, you see they are quite small and not very dramatic, just a small shift in the phase and amplitude. But exactly these features are where a lot of information is contained. And these small differences are due to a number of rather generic phenomena. For example, due to spin-induced multipole moments, which means when the neutron star is rotating, it kind of has a rotational flattening, if one thinks in Newtonian terms, and that impacts the gravitational wave signatures. There's also a signature due to the fact that a black hole has an event horizon, whereas a neutron star does not. And what I want to focus on in this talk, several kinds of tidal effects. And all of these phenomena are very generic. They occur for any object. What specifically sets the size of the imprint in gravitational waves and depends on the nature and internal structure of the objects are certain characteristic coefficients. So let me give you an example of such a characteristic coefficient, which is called the tidal deformability. So the idea is that when a neutron star, let's say it's non-spinning for simplicity, so when it's in isolation, it's completely spherically symmetric, and also that means its exterior space-time is spherically symmetric. But in a binary system, there's now a tidal field due to the companion, to which the neutron star responds by adjusting its matter distribution, so it deforms. But for gravitational waves, we are always interested in quantities related to the space-time. So we look at how does the space-time deform away from a spherically symmetric space-time. And in the adiabatic limit, that deformation is directly proportional to the strength of the tidal field, which makes sense. If you have a stronger tidal field, there should be more deformation. But there's a certain characteristic proportionality coefficient, which characterizes basically the stiffness of the material, and that is called the tidal deformability parameter. And it vanishes for a black hole, but for a neutron star, it depends on the internal structure. And this dependence is illustrated here. So in this slide, we start on the lower left, where we have all of the interesting microphysics that we ultimately want to understand. And from that, one can compute different equation of state models, which means the pressure versus density relationship. And currently, we have some constraints on the equation of state based on our understanding of nuclear physics and maybe some extrapolation on the low density side. And on extremely high density side, we have perturbative QCD calculations. But neutron stars cover the range in between those two limits, so there's still quite a large uncertainty in the equation of state. So here I'm just showing a few models just for illustration. It's not a complete list. And then taking this equation of state, one can go through the Einstein field equations and energy momentum conservation and compute tidal deformability versus mass for the resulting neutron stars. And in this tidal deformability versus mass curve, okay, this deformability has some weird units not shown here. But what you should just take away qualitatively is that each point on the curve corresponds to a different neutron star with a different central density. And each curve itself corresponds to a different equation of state. So that shows that measuring this deformability, one can work backwards to the equation of state, and preferably one would measure the deformability for different mass neutron stars, so one does not run into severe degeneracies that might occur at one point when, for example, two of these equation of state curves cross. And just to mention, so what is this calculation that goes into this arrow? Well, so usually if one takes this setup, as I showed on the previous slide, at face value, and one would compute stationary perturbations or static perturbations to an equilibrium neutron star and from an external tidal field, and see what is the resulting deformation of the space-time and how does it depend on the interior structure. But it turns out the same type of information can also be obtained by not considering stationary perturbations, but instead wave scattering perturbations. So that has some advantages. And if you're interested in reading more about this, there's a recent paper led by one of my PhD students that is listed here. Okay, so back to now the effect in the gravitational waves. So we have said now, okay, in a binary system, the neutron star deforms in response to the tidal field of the companion. But now we have to consider what is the effect of this deformation on the binary dynamics and on the emitted gravitational waves. So first of all, some energy now is needed to deform the neutron star. So that changes the energy of the total system. Also, these moving tidal bulges, they are phase coherent with the orbital quadrupole, so they contribute an extra bit to the gravitational radiation and the energy losses. So then one can get an approximate gravitational wave phase evolution by balancing the energy radiated in gravitational waves with a change in energy of the system and working out all the algebra to linear order in the tidal effects. One finds exactly this phase change due to tides is proportional to this tidal deformability parameter. It also scales like a high power of the orbital frequency, which means the effect is largest when the two objects are close together and orbiting very fast. And it is also suppressed by 1 over the total mass of the binary to the 5th power, which means for a neutron star and a very massive black hole, this effect is quite small. One more thing to notice is also that if there are 2 neutron stars in the binary system, there's a certain combination of the masses and tidal deformabilities that is easiest to measure with gravitational waves when one does not make any further assumptions. And this is often denoted by lambda tilde. It's just a combination that arises at the leading order and is similar to the chirp mass, which is a kind of weird combination of the individual masses that is also easiest to measure for long inspiral signals. Now, this kind of sketched out for you the basic idea of how the internal structure of the neutron star ultimately gets imprinted in the gravitational waves through these tidal effects. Now, for the actual data analysis, of course, much more sophisticated models are needed. So there has also been a lot of work over the last years to include more detailed descriptions of tidal effects with higher order relativistic corrections in full black hole baseline models that include already a lot of effects for point masses in GR and so on. So it's also very important for us to have different approaches to computing theoretical models so we can quantify systematic uncertainties. So taking then all of these models that include tidal effects, one can wait for an exciting gravitational wave event to happen. And this, in fact, occurred for the first time on August 17 in 2017 with the event GW 1708-17, which was a binary neutron star inspiral event seen in both LIGO detectors, and Virgo did not have a signal to noise ratio above the threshold, but that also gave a lot of information on the location of the source in the sky. But what this signal was a binary system at a distance of about 40 megaparsecs, so quite close to us for gravitational wave sources, with a total mass of about 2.8 solar masses, so two neutron stars of about 1.4 solar masses. And in gravitational waves, only the inspiral was seen as they were still orbiting each other. Then the merger and beyond occurred at too high frequencies where the detectors were not so sensitive. But we did have a lot of information from spectacular ranges of electromagnetic counterparts, which occurred as the two neutron stars, which have all this complicated subatomic physics. They were smashing together at close to the speed of light. So a lot of complex dynamics was happening, leading also to matter outflows of different kinds and many different kinds of electromagnetic signals. So what did we learn from this event? Well, from the gravitational wave side, it was a first opportunity to actually put experimental constraints on tidal deformability parameters of neutron stars. So this is what you see in the left panel here. The right panel shows a second event for which there was also some, it was also thought to be a binary neutron star, but it was much farther away from us, so the measurement was not as accurate in terms of the statistical uncertainties. And what you see in the plot is on the horizontal axis, this combined tidal deformability parameter lambda tilde that I mentioned before. And the y-axis is just a posterior distribution function. So basically, anything within these 90% credible intervals that I indicated with these orange columns, so any value of lambda tilde within those columns is consistent with the measurement at that confidence level. There's, as you can see, some width to these 90% intervals due to different waveform models. But so far, the modeling uncertainties, at least as far as could be quantified with the models available, they were subdominant to the statistical errors. But this, is of course not going to be true in the future, necessarily. On the right plot, you see the other event, which only gave a 90% upper limit. In both cases, I'm only showing the results when assuming a low spin prior. So assuming a priori that these neutron stars had a dimensionless spin of less than 0.05, which is consistent with what one would expect based on the population of galactic binary systems. But this is the assumption that also goes into this. Now, as I mentioned, then given this measurement, one can work backwards to the equation of state. And there have been a wide range of papers that I cannot go into because they looked at many different aspects of what do these measurements, what implications do they have for different questions in subatomic physics of neutron stars. So I just want to show you one result that could now be addressed. For example, if one takes together constraints from the gravitational waves, from the electromagnetic counterparts, which also depend on some properties of the matter, as well as recent measurements of neutron star radii and radio pulsars, and so on, one can ask, well, given we have all this information, if we take it all together, what can we say, for example, how large is the pressure at a given density? And here, this was just say, let's say at 1.5 times the nuclear saturation density. And so here again, this is a plot of a posterior distribution function, this time for this pressure at 1.5 nuclear density. It's just a fiducial density that to illustrate the constraints. And the different colors here are in dashed different ways to extend the nuclear physics knowledge to a bit higher densities by including multi-body neutron interactions and so on. And in solid are the corresponding posteriors. And you can see that, yeah, there is now some information in the data because it's, yeah, the posteriors kind of start to a little bit converge onto common values. There's still quite some uncertainty and still some dependence on the priors, but it's an exciting first step for what we can expect with in the future. Once we have more accurate data, this will become better constrained. Yeah, so this was for the constraints and recent discoveries, but I also want to touch upon a bit that what I've described so far was only kind of a tip of the iceberg of what kinds of rich matter effects one can have in binary systems. And here in this talk, I cannot describe everything because it is really a rich system of having all of this complicated matter physics interact with dynamical strong field gravity. But I just want to mention a few additional considerations. So first of all, if one thinks a bit in more detail about these tidal effects that I mentioned. So if we think from the point of view of the neutron star in a binary system, it sees the companion orbiting around and exerting a tidal force that changes on the orbital timescale. But as the orbit shrinks due to the gravitational wave back reaction, the tidal forcing frequency also sweeps over a wide range of frequencies, and that might pass through a resonance with one of the internal modes of the neutron star, where the neutron star has actually a wide spectrum of characteristic modes because it has such a complicated internal structure. And several of those have low enough frequencies that they could be fully resonantly excited in an inspiral. So this is one scenario that can happen, which would be highly interesting because such kind of mode resonances, they are kind of spectroscopic probes of neutron star interiors of really details that are very difficult to extract from sort of more integrated quantities like the mass and radius of a neutron star. But even if the excitation is not fully resonant, taking into account that tidal effects correspond to some excitation of modes, that can lead to a significant imprint in the gravitational waves. And that was in fact what I described before. This global deformation of the neutron star is fundamentally actually due to its so-called fundamental modes of oscillation. Except they're not resonantly excited, and at least not significantly for circular orbit inspirals. And so one doesn't see any oscillations. It's just that the resonance is extremely broad. So as one approaches the resonance, it becomes noticeable that there is a mode and not just a static deformation. And this is to make it more concrete, is illustrated here in the plot below, which shows on the y-axis some measure of the response of the neutron star, so Q divided by E, versus frequency. It's for a fiducial case, so the numbers don't matter so much here. Just that the horizontal dashed line is the static case. If one assumes from the beginning, it's simply a static deformation. And the solid line is when one takes into account that this deformation is actually due to the fundamental mode of the neutron star, where the mode resonance is not shown on the plot, but you see even far from the resonance, there's still a significant enhancement of the response compared to the purely static case. And this response is also not only impacted by the physics of the neutron star itself, but also by relativistic effects such as the redshift and the frame dragging effects. And furthermore, it is also impacted by rotational effects, both from the spin of the companion and from the spin of the neutron star. Okay, so now that I've mentioned the spin of the neutron star, I also want to give you one more example to highlight how rich all of this physics is. Because when we think about a rotating neutron star, it also has different other types of modes. And this is because, similar to the Coriolis effect in the Earth's atmosphere, which causes some circulatory spiraling motion of the air masses, similarly in a rotating neutron star, there are characteristic modes that also induce a kind of spiraling circulatory fluid displacement. And the key feature of these modes is that their frequency is proportional to the spin frequency of the neutron star. So invariably, at some point during the inspiral, maybe outside the detector band, but nevertheless somewhere, they will be fully resonantly excited. And how are they excited? Well, the strongest coupling is actually not to this EIJ tidal field I showed before in the context of the fundamental modes, but instead it's to a different piece of the space-time curvature produced by the companion, which is more analogous to a magnetic type field. And it corresponds to a frame dragging field, so it has no Newtonian analog, and as a result, these modes have several interesting and maybe unexpected features. So now that we have discussed a bit of what additional considerations should go into tidal effects for neutron stars, let's also consider now the challenge of describing how all of this could affect the binary dynamics and ultimately the gravitational waves. And the idea is that when we want to describe what happens to the binary dynamics at large separation, basically the neutron star looks like a point mass with some small multipolar corrections. So in a relativistic language, that would be a world line and some multiple moments. And here we are just considering two linear order in the spin. So the multiple moments are, for example, the mass of the neutron star, the spin, and then all of these tidal moments, where there's now some mass multiple moments and also current type multiple moments.
Hello, Tanja?
And so on, but this is not included here. And of course, here we also specialize only to the quadrupole tidal effects. So to describe this system, it is then useful to use an effective action approach, which gives you a single scalar function from which one can derive all of the dynamics. And how does this effective action depend on all of these quantities? Well, first of all, there's the point particle part, which describes the center of mass motion. And then there are these additional finite size effects. And those arise from the fact that the multiple moments of the neutron star interact with the companion's space-time curvature. So the interaction depends on if it's a mass moment or a current moment, but is a similar coupling. And then, as I mentioned, one has to take into account the spin of the neutron star, which gives rise to the Coriolis effect, which impacts both the fundamental mode resonance response and provides the restoring force for the gravitomagnetic modes. Also, there are some frame dragging interactions, which come from a variety of sources. First of all, the angular momentum associated with the tidal quadrupole moments interacts with all the other angular momenta in the system. So that, for example, the angular momentum of the orbit and the spin of the companion. And then there's also the internal dynamics of the multiple moments, which, as we said, are due to the or are associated with mode excitations, so they behave a bit like harmonic oscillators. So then we need to write down, how do these harmonic oscillators behave? Well, you can see here for the fundamental modes, it looks really like a harmonic oscillator, except now with some more tensor indices and some relativistic effects taken into account, but you can clearly see there's a kinetic term and then the elastic potential term. And what is noticeable is that these characteristic tidal deformability parameter and mode frequency, which encode the internal structure, they appear here in this action as coupling coefficients. So this is for the normal mass multiple moments, but for the current moments, actually, as I mentioned, they have some unusual features. So actually, the harmonic oscillator type description has a kinetic term as well, but then there's no elastic potential term. Instead, there's a nonlinear field contribution. And furthermore, there are also two kinds of tidal deformabilities associated with these modes. And actually, both of them play a role. So that this gets quite interesting. But I do not want to go into further details here. This is just to give you a flavor of some of the considerations and then also the framework that then goes into calculating the effect in the gravitational waves. So now, of course, the question is, how well do these theoretical considerations agree in practice with, for example, fully numerical relativity simulations of inspiraling neutron stars? And one thing to keep in mind is that the numerical relativity simulations also have several difficulties. For example, resolving the scales of the matter inside the neutron star and doing very long inspiral simulations. So actually, there's not so much hope at the moment to see these gravitomagnetic effects. Instead, one can focus on the fundamental mode effects and then say, well, if those agree quite well, then that it gives some indication that the theory is relatively solid. So there's also some more evidence that maybe other theoretical descriptions work quite well. Or of course, one can turn it around and say the theoretical considerations come from physics, so one can use them to test the numerical relativity simulations. Or at least benchmark is probably a better word. So in any case, if we compare the analytical models to numerical relativity simulations, there have already been many comparisons done also by different groups and using different models and codes and results. So here is just one example of this. And it shows the phase difference in gravitational waves versus time. And the phase difference is between different models and the numerical relativity waveform. And in gray here, you see the indication of the error in the numerical relativity data. So you see for most of the inspiral, which goes from left to right here, the models remain within the error bound, so they are consistent with the numerical result, but towards the very end, some of them at least go outside of the error by some small amount. So that indicates, at least the description is reasonably good. Of course, there should be improvements for the future, but it's a good first step. And similarly, one can say for two neutron stars, how does it change if one takes the same system, replaces the black hole by a neutron star? Then, of course, the matter effects are much larger because two bodies are contributing. And also towards the very end of the inspiral, the physics is a bit different than for neutron star black hole cases because the matter distributions of the neutron stars can start to overlap a bit. So now this was for non-spinning cases. So now let's consider including the spin effect, which I said before for the fundamental modes that also impacts the response because it shifts the resonance away from the F mode resonance that would be excited by the same frequency in a non-spinning case. And here the plot shows the phase difference compared to the phase difference in the non-spinning case, because as I showed previously, in some cases, there can be a bit of a phase difference already with the models in the non-spinning case. So subtracting that off to really focus on how well are the spin effects of the neutron star on the tidal response modeled. We can see here that including this Coriolis effect on the fundamental mode, the models remain relatively close to a zero difference for different values of the spin and different equations of state, which is what the different colors are. And in dashed are models that do not take this into account, which show a much larger spread. So that gives some indication that the theoretical description, including this Coriolis effect and fundamental modes, is a good step forward, but of course it is not conclusive evidence. And one more interesting thing, let me actually just check the time. Okay, I should probably wrap up now. So just to say many more interesting things to be learned. And also in terms of experimental data, an exciting future is ahead, starting already at the end of this year, probably, when the next observing run will start again of LIGO Virgo, and now also Kagra in Japan is joining the network. So we expect to have much more sky coverage and prospects for localizing sources, and also longer times where at least two detectors are taking data and don't have a downtime. So overall, these detectors will also be much more sensitive, so enable more accurate measurements of nearby sources, and also just a much greater population and diversity of events, including hopefully also some of them that are either double neutron stars or neutron star black hole. And then in the longer term future, the community is currently also preparing for this. And in Europe, there's a plan to have a so-called Einstein telescope detector, which would have 10-kilometer long arms in a triangle configuration underground to eliminate seismic disturbances as much as possible. And this would have 10 times better sensitivity than LIGO and Virgo, so would actually detect hundreds of thousands of binaries per year. So a whole slew of signals, and also then really high precision studies of nearby sources. Furthermore, it would have a wider frequency range, which has many advantages. First of all, to measure what happens when two neutron stars really collide and afterwards, or a neutron star gets tidally torn apart by a black hole. Also for the low frequency improvements that would enable early alerts for electromagnetic observatories to point telescopes and catch the full spectrum of electromagnetic counterparts. In the US, there's a similar vision. It's a slightly different configuration to basically have 40-kilometer long LIGO instruments in essence, would have similar sensitivity. And of course, it would be best to have both the Einstein telescope and this cosmic explorer operating at the same time, and preferably also at the same time as a space-based detector called LISA. But to take full advantage of all of the information encoded in the data of gravitational waves, once we have more accurate measurements, we also have to really improve the theoretical modeling and the interpretation of the measurements. So a lot more work remains to be done to improve the theoretical models. Of course, even for these highly sensitive instruments, not all of the microphysics is important, but there are some more effects that need to be taken into account. Also, we need to be mindful that there could be possible degeneracies between, for example, modified gravity or dark matter beyond standard model physics and these matter effects of neutron stars. Also, in terms of the interpretation, how do these gravitational wave parameters relate to fundamental physics, and how can we best combine with interdisciplinary information that is coming from all the exciting developments, for example, in astrophysics, from NICER, from radio pulsars, as well as from electromagnetic counterparts, also from the nuclear physics side, QCD. So it's really a vibrant interface between different fields. So let me just summarize. I hope I've conveyed that neutron stars are extremely interesting for probing different aspects of subatomic physics, both for fundamental QCD physics and for understanding the emergent phenomena at the subatomic level. And gravitational waves are very promising probes of this physics. We expect a lot of exciting data to come in the future. But to really optimize the science gains with that data requires also better modeling or more accurate models, and also connections with other information. So with that, I would like to thank you very much for your attention and would also be happy to take any questions.
Thank you very much, Tanja. Thank you. And indeed, it's time for questions. So you can raise your hand or write your question in the chat, and Irina and I will check. So for the time being, I don't see any question.
Can I ask a question while the others?
Yeah, sure, you can, Irina.
So thanks for the wonderful talk, Tanja. So I have the following maybe general questions. So so you showed this this comparison between the numerical and the analytical waveforms. Which kind of precision would you need to analyze data from Einstein telescope?
Yes, yeah, that depends, of course, on what kinds of sources we would see. I mean, if there's another source like GW17 or 817, then we really need high precision waveforms. I don't have the exact number for this, but yeah, already there were some studies by Tim Dietrich and collaborators that even for advanced LIGO design sensitivity, the systematic uncertainties in the modeling could become a problem. And that includes not only the matter effects, but also the underlying black hole baseline model. Yeah.
So for Einstein telescope, that will be completely, so you'll need
yes.
Okay. Thanks.
Any other question? So before, yes, there is a question by from Michel. Michel,
yes.
You can ask.
Yes, Tanja, sorry, I maybe missed it in your, can you show again your slide for the 04 one? Just
yes. Yeah, I did not give much information here.
Yeah, but that's what I would ask, if you can give a little bit more in terms of better sensitivity, and when will it start exactly? End of
yes.
this year? Or?
Yeah, so the plan, as far as I know, is near the end of this year. It should start again. As you might, I'm not sure if you heard this, but the third observing run actually had to end early because of the pandemic.
Yes.
But now they have been upgrading the detectors further. And yeah, so the last I heard was at the end of this year, they plan to turn on again LIGO and Virgo. I think actually CAGRA and GEO600 are operating at the moment, but I'm not sure. And yeah, so the goal is that these detectors should start to be near the design sensitivity, and probably, so the run is probably 1 year or so. So over the course of this run, they also plan to improve the sensitivity and probably get near or at the design sensitivity.
Yeah, is that a gain of sensitivity by what? A factor of 2, factor of 5, with respect to O3?
Yes, so I think with respect to O2, it's a factor of 2 in sensitivity, but I'm not sure about these numbers. But it will be quite a significant improvement.
Yeah, thank you very much.
Thank you. So is there any other question? While waiting for a question, maybe I can ask a quick one. To me, as I understood it, the dynamical tides are important even now for LIGO Virgo, at least the Newtonian effect, the leading order effect. I would like to know if already for the current measurements, or at the 04 measurements, let's say, it will be important to include certain of the relativistic effects you talked about beyond Newtonian order.
Yeah, so this study has not been done yet. Yeah, so I also cannot really say any concrete information. It also depends what kind of relativistic effects one is considering. Which ones in particular were you referring to?
Anything. So for instance, I don't know, the relativistic corrections to the quadruple dynamical tide, for instance, the 1 PN correction to that. But whatever.
Yes.
It's a general question. It's just to have an idea of the accuracy we need. So do you do another way to ask the same question? Do you think staying at Newtonian order would be enough for those effects for, I mean, in practical purposes in the near future?
No, probably one needs the relativistic corrections. I mean, this was already the case with just the adiabatic tides, where the 2pn corrections do make a significant difference, for example.
Okay, I think this answers my question. Thank you. So any other one? I don't see perhaps in the chat, no. Okay, so perhaps then I can ask another question,
Yes.
since I don't see anyone asking. So, but it's a bit more technical, so I hope it will not bore the audience. It's just I was curious to know how you generalize precisely, for instance, Qij, if you go beyond Newtonian order, because it seems Qij as it is originally it's defined is a Newtonian quantity. So how would you define it beyond that and parameterize the difference to sphericity in a, let's say, in a covariant like way, or how you do that?
No, so Qij is really defined fully relativistically.
Yes, and so how do you do that? So is it?
So we model the neutron star fully relativistically, but with small tidal perturbations from a distant companion. And then we extract what is the Qij. And then we have this fully relativistic effective action here, which also relies on the same Qij. Well, okay, the identification is a bit subtle maybe, but in any case, it also is, this action is fully relativistic. It's just once you start to plug in what are really these tidal fields and all of these terms that one has to make some approximation or use some post-Newtonian expansion.
I understand. Okay. Thank you. So, yes, there is a question from Robert, so you can go ahead.
So thank you for the nice talk. Yes, I have a question. Can you learn something different from a neutron star black hole binary compared to a double neutron star binary? Is there something different in the diagnostics you can make and the information that you can obtain?
Yes, that is an excellent question. So, okay, ignore please the plot here. I just focus on the cartoon, which shows what is unique for neutron star black hole systems, which is that it can happen depending on the parameters of the binary system. It can happen that the tidal force from the black hole becomes stronger than the self-gravity that is holding the neutron star material together. So the neutron star can really get tidally ripped apart, which you see here. The kind of colors indicate some density distribution of the matter. And then it is accreted onto the black hole, and some matter may also remain outside. But the feature in gravitational waves that comes from this process is that all of a sudden, as the neutron star is disrupted, the gravitational waves just end. You see an inspiral, and all of a sudden the signal ends. And that is characteristic of this tidal disruption. And the frequency at which that happens also depends on the properties of the neutron star matter. And whereas for two neutron stars, the merger, once they collide together, then different outcomes are possible. It's possible that they immediately collapse to a black hole upon merger, or they form some sort of hypermassive neutron star that is highly oscillating and rotating and still emitting gravitational waves, and then it collapses to a black hole because after some time it might have lost too much angular momentum to stabilize the matter against the gravitational collapse. Or the double neutron stars can collide and again form some very dynamical oscillating mass distribution, and which then slowly settles down to a stable neutron star. So these are kind of the main differences.
Okay, thank you. There has been a couple of black hole neutron star binaries which have been already observed. Has it been possible to obtain such information, or the signal was not good enough?
Yeah, so there were two neutron star black hole. Let me just see if I have some slides. Yes, let me see here. Yeah, so oops. Yeah, maybe you can see it here in the skipped slide. So these two neutron star black hole events were called, they were observed in January of 2020. And so one of them was about a 9 solar mass black hole with an about 2 solar mass neutron star or smaller object. But the black hole spin was quite small. And the other one was a lower mass black hole, 6 solar masses roughly, and a 1.5 solar mass neutron star. But in this case, the black hole spin was anti-aligned. So let me just see if I have a picture here. Okay. Yeah, no, I don't have it. But basically the point is, for these kinds of systems, one would also not expect this strong tidal disruption of the neutron star to occur. And yeah, they also had low enough signal to noise ratio that all of this was not measurable. So for these events, actually, one could not even tell if the smaller object was indeed a neutron star or not. They looked just like, 2-point masses.
Okay, thank you very much.
So thank you very much indeed. And I think it's time to conclude. So thank you for the talk and for staying to answer those questions. And perhaps see you in presence in some time in the near future. Yeah. Goodbye to everybody.
Thank you, Tanja. And
thank you for the invitation and for the discussions.
Okay.
Bye.
So goodbye.